Hi, welcome to this video. My name is Phil and I'm a senior lecturer in astrophysics at the University of Lincoln, and I want to go back to galaxies yet again and also back to elliptical galaxies. But this time around I want to have a look at the ellipticity profile and what that is, how you calculate it and what it actually kind of means for these particular type of galaxies. Now, if we kind of go straight back to the tuning fork diagram, the Hubble classification system for galaxies, we have spirals on the right-hand side. Now, depending on which version you see, you may see like 2 pathways, you may have 3, there might be an additional one in the middle. But basically, these are spiral galaxies that have spiral arms, they're disk-like galaxies, they have lots of gas, they obviously lose their gas or they deplete their gas as they age, their spiral arms become more tightly wound and they get slightly redder, but they obviously have features, they're not kind of completely smooth, so they have these spiral arms and they would essentially on this diagram here evolve from right to left. But we're not interested in spiral galaxies for this video. We're interested in the elliptical galaxies. Now these are on the left hand side of the Hubble galaxy classification tuning fork diagram, and these are mostly defined or classified by their shape, and they can go from spherical like to more kind of cigar shape, so they kind of have this E number, so E0 to E7, although to be perfectly honest, the ones that are quite elliptical, so E7, E5, those sort of ones, are unlikely to be true elliptical galaxies. They're more likely edge-on lenticulars. But anyway, we're interested in these elliptical galaxies. Now, generally, elliptical galaxies are smooth and symmetric. They're not like spiral galaxies. And I say generally, that's not always true. They do sometimes have some features, but if we're talking just fairly generically, elliptical galaxies are typically characterized by being quite smooth and they are symmetric, whereas a spiral galaxy is not smooth. It has the spiral arms where they're brighter and then dimmer regions in between. So this is important, smooth and symmetric. Now, we have these things called isophotes, and this basically is a line or a curve that connects points of equal brightness. It's a bit like a contour line. So if we draw a line around our elliptical galaxy, that line or the isophote line would be the same surface brightness all the way around. And for an elliptical galaxy, because they are smooth and symmetric, you generally kind of get these ellipses, or if it's a perfectly circular elliptical galaxy, more spherical, then it would be more like a circle. But anyway, they basically trace all the way around. And as you go further out, you'd get another isophote and things like that. But with elliptical galaxies and galaxies in general, they're typically brighter in the centre than they are on the outer part. So as you get further out, they get dimmer. So you do basically have these collection of ellipses basically that trace out the surface brightness. So to calculate the ellipticity, hopefully I've pronounced that kind of okay, you need to look at the major axis of the ellipse and the minor axis of the ellipse of the isophote. So here we have like the major axis, which is A, and the minor axis is B. And to calculate that, we basically divide the minor axis by the major axis, and then we subtract that away from 1. And that gives us this ellipticity number. To give you an idea of how it might work, if we had a spherical isophote, we're kind of looking at it so it's more circular, but let's assume that it's a sphere, so it's symmetric all the way around in all directions. Then your A and B are going to be the same. So basically we end up with a 0. So the ellipticity is 0. Now if we then increase our major axis and leave the minor axis the same, so if we double the major axis in comparison to the minor axis, then we end up with a ellipticity of about 0.5. Now what we're going to do here, or what the ellipticity profile does, is it measures this ellipticity for the isophotes as you move out from the centre. So basically, to get the profile, we calculate the isophotes and their ellipticity from the centre, and we go further out and we get a value for ellipticity as a function of the distance from the centre, which would be r. So when we do that, and we can then create a plot, which is then the ellipticity profile. So if we have the distance from the centre of the galaxy, we then basically trace out the isophote at that location, We then calculate its ellipticity due to the major and minor axis, and we get a value for that. And if we do that all the way out, we'll get some graph. Now I've just put a linear graph here. That's not necessarily true, but they will typically kind of increase as they get further out. So this is just for visualization purposes. It's not typically going to be a linear response like this, but we do get this ellipticity as a function of distance. So generally, for most galaxies, what we typically see is that the ellipticity increases with distance. So what does that actually mean physically? Well, it means that the outer parts of the galaxies, the isophotes, become more elliptical. And in the centre, they're kind of closer to being circular. And that's a general rule for quite a lot of these elliptical galaxies, that they generally increase and have like a positive relationship between the ellipticity and the distance from the centre. However, every galaxy is completely different. They don't have a set profile, and if you calculate this out for each galaxy, they will be quite different. So here I've got two different galaxies. Now the red one is probably more closer to what it might be, so you might kind of see this non-linear increase that kind of smooths out with distance. You've then got the yellow one there where it's kind of a bit bumpy. Again, these are all plausible, and each galaxy is going to be different. And these are some examples actually of two galaxies we've got here. So the top one there, you can see it's kind of more, it kind of tapers off, it increases and then tapers, settles out towards the outer part. Now this is given in arc seconds, which is like an angular size. Same thing really, it's the distance from the centre. Doesn't necessarily matter too much on what the units are. And then the one at the bottom, the green one there, you can see that's a bit more bumpy. And it just depends on the properties of the galaxy and things like that, but they don't all have the same. They will all have their own unique ellipticity profile. Now, it's quite convenient to actually calculate a single value for a galaxy. So we don't typically, we can calculate the profile, but it's just for convenience sake, we might want a single value for that particular galaxy of ellipticity. So what we would do here is we would calculate the ellipticity at the effective radius. So what's the actual effective radius? Well, the effective radius is the distance from the centre that contains half of the galaxy's light. Now again, I've just illustrated this on this galaxy here that isn't technically true. It's just, you basically do the isophote around the effective radius, which contains half of the galaxy's total light that it's emitting. So by doing that, we can then get like a single value for the ellipticity for that particular galaxy. Now, that's quite interesting. So we can work out how essentially the ellipticity changes as a function of distance. Most of them are showing that they get more elliptical towards the outer part. But also, we can look at the angle between those isophotes as well. So that if they're all perfectly aligned, then it will look like on the left there. So all those elliptical isophotes have the same major axis, but you can get a twisting occur. So on the right-hand side there, the isophotes, as you get further out, actually there's an angular rotation between them, and it's called isophote twisting. And generally that's seen more in the outer regions of a galaxy than the centre parts, although I probably should have illustrated that slightly different on the picture, because it looks like the centre part's been twisted, but I should have probably rotated it around and made the outer part twisted. But it's typically the outer parts where we see this isophote twisting occurring. Now, what might be causing that? Well, actually, a lot of these may be interacting with other galaxies nearby, so tidal interactions, gravitational distortion, which is distorting the outer parts of the galaxy, maybe even past mergers and things like that, could actually twist and distort the isophotes so they actually appear to be twisting. So thank you for watching. If you enjoy the videos and find them helpful, then do consider becoming a member of the channel. There's extra videos in the member section, and also it generally helps support the channel and make these videos. So thank you for watching.